The topic that of today is using anisotropic interactions. This is really the dipole-dipole couplings and chemical shift anisotropy to study dynamics, especially under magic angle spinning NMR. But we'll talk a bit about a few different aspects of the things that are related to this. So I'll just give a quick overview of what I want to talk about today. So of course, we want to talk about how we are going to measure these, how we are going to use these anisotropic interactions to study dynamics. And my focus is going to be on dipole-dipole couplings, but we'll briefly touch both quadrupolar couplings as well as the chemical shift anisotropy, the two other anisotropic interactions that can be used to study dynamics. Of course, I will compare this with how you can look at isotropics. What's the difference between looking at isotropic interactions versus anisotropic interactions for studying this dynamics? And the two different classes of experiments that I want to kind of touch on. One, mainly the read-or and other decoupling. Read-or means just the measurement of dipole couplings. That's what I mean over here. And we'll look at a bit of the theory of it, some of the experimental regimes which you can access this kind of measurement techniques, and some of the technical challenges, the solutions for which are emerging slowly, and then look at some of the examples. And later on, I want to touch, build up upon whatever we have learned about this reader and look at the codex experiment as an example, how to do slightly more than whatever is available with reader experiment. And then if time permits, we'll have some additional things at the end. Right, so let's start. And I don't think I need to convince this audience that measuring dynamics is important. The reason I put this slide over here is just to highlight that many of the things that I'm going to talk about today have their origin in my own research. I mean, I'm interested in these things because these are very important for the kind of systems that I study, which is primarily biomolecular solid state NMR. So we're interested in things like how the dynamics of these loop regions over here will change the access to this cavity, and how will it further change the structure and activity of this protein, or how transmembrane proteins change the orientation of their transmembrane helices to allow the coupling of various ions, the movement of various substrates and ions through these channels. So although my focus is on biomolecular solid state NMR, whatever I'm going to talk about today, of course, doesn't necessarily have to deal with biomolecular solid state NMR. You can think of this being applicable to a large variety of systems, materials, polymers, what have you not. For example, you can think of this thing as an exchange between some solvent at the surface of a silica nanoparticle, and you can use some of the same techniques that we are using over here to study, for example, the dynamics of these solvent molecules, their interaction with the surface, and so on. And again, you can just plug in any system that you kind of want to study, and some of the techniques that I'm going to talk about today should be useful in those contexts as well. And of course, as we know, NMR has a leg up on trying to look at dynamics on a variety of time scales. That's because we have a lot of different interactions, and a lot of interactions can vary in magnitude by quite a lot. For example, our frequencies are going to be several hundreds of megahertz, while the interaction tensors that we measure, the quadrupolar tensor or the dipolar coupling tensor, or the chemical shift tensors, are going to be a couple of orders of magnitude lower in value, a few kilohertz, few tens of kilohertz. And then we also have the isotropic interactions, which is the isotropic chemical shift, and the scalar couplings, which are going to be even slow. So the nice thing about NMR is that you can access, because these interactions span a fairly large range of strengths. You can tune, you can sort of change the experiment that you want to do if you are looking at a completely different time scale. The two other things that you have under your control are the RF field strengths. So this is another interaction over here, which can span anywhere from a few hertz to hundreds of kilohertz again. And the magic angle spinning frequency, which we will come to in a bit, which is primary focus. Just to keep the numbers in mind, when we talk about solution NMR, we normally compare what the molecular rotational collision times are, and they can be of the order of few tens of nanoseconds. So the biggest, so to say, proteins that have been studied in solution NMR would be of the size of a few 60, 70 nanoseconds. That rotational collision time would be approximately this much. When we talk about solids, we deal with time scales. The overall rotational correlation times are going to be much smaller, and in fact, in most of the cases, there is no overall rotational correlation time. Magic angle spinning is what gives you a coherent motion, which is kind of different from this motion. So we have effects depending on what the dynamic time scale of the dynamics you're looking at. You're going to have effect on different frequencies. For example, the molecular rotational over here has an effect on the Raman frequency. So you have a lot of T1 relaxation processes going on because of the motion in this time scales. Whereas if you look at microsecond or even millisecond dynamics, then you expect them to have effects on your coupling tensors, as well as, if it's much slower, then maybe the isotropic chemical shift. So how does dynamics really affect these interactions? So when we measure these interactions, we measure them, for example, when we look at simple isotropic chemical shifts. There have been very well established models of how fluctuations in the isotropic chemical shift can cause spectra that look completely different. So starting from the Bloch-McConnell model for chemical exchange, what we can sort of see is any compound. Doesn't have to be a bimolecular compound. In this case, this is a small carbene precursor, where you can see that this R, which is an isopropyl group, at very low temperatures exists in two different conformations. But as you increase the temperature, where this bond rotation increases, you can have these two peaks sort of coalesce into a single peak at the average position of these two. While the same isopropyl groups over here will merge into this peak over here, which is even at this temperature is quite broad. You can do all of this as a function of temperature. You can have very simple Arrhenius kinetics, or you can fit it to the Eyring equation to get some clues about how molecules might be in their excited state, what might be the energy, what might be the barrier for this rotation. And so it's a very rich area of that you can utilize to really understand your molecules solution. Of course, it's not just limited to that. There are several different classes of experiments: relaxation dispersion, CEST, line shape analysis, which is what this is, or even exchange spectroscopy that will allow you to look at the fluctuations in your isotropic chemical shifts in order to come up with some model of relaxation for dynamics. Of course, these fluctuations not only have effect on the isotropic chemical shift, they also cause a relaxation. And typically, when we think of solution NMR, that's what we measure. So, for example, your T1 rho, or heteronuclear NOE, or T2 primary relaxation times tell you something about how the overall molecule tumbles in the solution as well. However, in solids, of course, this is perfectly applicable to solids as well. And in fact, we do quite a bit of experiments where we look at chemical exchange just by very similar techniques. Bloch-McConnell, for example, looking at the line shapes, as well as looking at relaxation parameters. There are several different classes of relaxation experiments under magic angle spinning and under static conditions, which look at the relaxation parameters and try to interpret it in terms of what the dynamic process actually is. However, in solids, we have an additional thing, which is the anisotropic interactions. And of course, it's not unique for solids. You can also think of this as being something similar to the RDC experiments that happen in solution NMR. So this is partial alignment. But in solids, of course, everything is completely static. There is no alignment, so to say, or there can be alignment, but in this case, you're not considering any alignment. So dipole-dipole couplings in chemical shifts and quadrupolar couplings to look at. Of course, the isotropic chemical shift is also there. So we'll ignore the relaxation part for a bit, but exactly the same way that we look at the isotropic chemical shift, we can also think of changes in the orientations and the magnitudes of these tensors that are important. So what we are primarily concerned with is when these tensors change orientation, how does it affect our measurement of them? And so for doing that, we must understand what these tensors are and how do they react to changes in either orientation or magnitude. So For simplicity, assuming that the tensor magnitude is not changing, what you are only looking at then is the changes in the orientation, which is the dynamics that you want to interpret. So these are all rank to tensors, and their spatial transformation is the same as the second order Legendre polynomial, which means that the term that we are always going to be worried about is going to be the speed to cos theta term, which is equal to the 3 cosine square theta minus 1 by 2 term that I'm sure many of you might have seen before. And what we are dealing with in solution MR is completely isotropic motion, which completely averages out this term. And if you just do an integral of this over the sphere, this is supposed to be not a circle, but a sphere. If you do an averaging of this, just the speed to cos theta term over the sphere, you will get a 0, which means that all of these terms completely go to 0 when you have completely isotropic motion. One of the simplest models in which we can think about dynamics is the diffusion in a cone model, where you have free diffusion inside the cone, and then the whatever it is, the bond vector or the tensor is not allowed to go beyond this cone. And deriving the average value of the tensor is slightly non-trivial for a cone. So I just put up this review over here. In the case of very fast diffusion, which means that you have very fast diffusion in this cone, diffusion that is faster in magnitude than the strength of the interaction that you are measuring, then you can come up with this functional form as the correlation function at infinity, which is 1/2 1 plus cos theta c. Theta c is this half cone angle times theta c. This will give you how much your interaction is going to be scale wise. So if you look at what this number is, it's going to go from between 1 and 0. This is the half cone angle going from 0 to pi by 2. So the magnitude of the order parameter goes from between 1 and 0, and it tells you, for example, how dynamic is the motion. So if the cone angle is extremely large, that means that you have free diffusion, for example, in one hemisphere, then your order parameter is practically 0. While if you have absolutely no cone angles, which is completely rigid bond vector, then you have order parameter of 1. And you can have any values in between. Of course, this is only true for diffusion in a cone model. It's not necessary that the kind of motion that you will see in your samples is going to be like a diffusion in the cone model. You could have, for example, a two-side jump model where you have two different conformers which are jumping between two conformations, either with same population or with different population, but there is a jump between the two sides. Or you have a three-side jump, for example, in methyl rotation, where you have where you have a rotation axis and the molecules jumping between three sides. Or you have some more complicated motion that you can sort of define in a rigorous manner. So the general case of this is that you will have to, at the end of the day, do a numerical simulation in which this multi-site jump is evolved simultaneously with your recoupling sequence. We will see what that is. And again, this is very, very similar to what we do in Bloch-McConnell models, except that it's slightly complicated because now you have magic angle spinning as well for most of the samples. So the paper from almost 20 years ago now, from Kai and Fishbach has details on how these simulations can be done. And you can also look up the recent review from Matthias and Paul Schanda, where they discuss all of these things again much more detail. So once you know this, so once we know what we're looking at, we want to measure these anisotropic interactions and then try and see whether the measured anisotropic interactions are what we expect them to be. For example, this is a case of deuterium. So deuterium is a quadrupolar nuclei, has a fairly weak quadrupolar coupling, so you can measure these things quite robustly. And we also know that, for example, in a methyl CD3 group, what the value of this quadrupolar coupling should be, just based on what the mechanical is. If you have a completely static case, you can measure the coupling in that region. So in this case, what we see is that if you have a methyl CD3 group, but you have a three-side jump between these three CD3, then the value of this quadrupolar tensor is quite dramatically. It is in fact 1/3 of whatever you expect it to be. And the line shape, again, the measurement of this line shape is very, very indicative of what kind of motion is present. For example, if you have a methyl rotation axis that diffuses So not only is there rotation, but there is diffusion of the rotation axis. Then you will get a curve that doesn't look like this, but something like what looks in P. Or you can have a much more complicated motion where your methyl rotation axis jumps in 4 different sides, and then you can have something that doesn't look like it has this big pattern like line shape, but something like this. And you can have even more complicated motion. For example, if you have the CD, the aromatic group, either in the meta or the ortho position of a phenylalanine ring. And if you have just a static case, then you will get this nice peak pattern. But if you have a flip of the aromatic ring, in an intermediate case, you will see these very strange looking powder patterns. So this is in the case of the intermediate motion, where if you have really fast pi flips, then you will get this very, very distinctive peak pattern. And this is again covered quite extensively in this review from some years ago. This is the case of the quadrupolar nuclei. You can also use the chemical shift anisotropy. Again, there are many, many examples. I'm just picking up one for quick demonstration. So, for example, here it's an N15 static spectra of uniformly N15 labeled protein, a GPCR, as a function of contact time. So if you have a cross-polarization and your contact times are very, very small, you're going to selectively excite only the rigid part of the molecules, and you're going to get only a very simple powder pattern from all of the backbone atoms in your protein. If you increase the contact time, there is a chance that you also transfer polarization to things that are highly dynamic. So you can start seeing some isotropic, some sort of sharp peaks over here, which would indicate the isotropics. And if you either look at either direct polarization or very long contact times, then you'll also see some, for example, side chains, which you expect to have a lot of motion in there to show up in these cases. One very interesting example of how dynamics can really completely change how your spectrum looks is this very interesting example from Tony Watts and Clemens Globulus, again, a quarter of a century ago, where what they did was aligned these membrane samples on glass plates and put them inside a rotor, where you see these are just glass plates, and then you'll have a single orientation of all of these helices over here. Now, what happens is that if you have a complete powder sample, then you will, this is just looking at the phosphorus head groups. So you'll get a very simple powder pattern from the phosphorus head groups. If you spin a bit slowly, this is about 2 kilohertz, if I remember correctly, what you'll see is the isotropic peak, which is marked by star, and then you'll have side bands. You can do analysis on the side band pattern over here and try to come up with this tensor back, and it should be this is a very, very popular way of actually trying to understand what the tensors are. Now, if you align this glass sample and the magic angle, so there's no actual motion in the sample, but there is internal motion in your sample. So the entire lipids are rotating, or any protein that is embedded in this bilayer is undergoing fast rotational diffusion. So it's like magic angle spinning without really spinning anything. So it's a static sample, but the protein itself is undergoing rotational diffusion. So in this case, if you do the experiment, what you will see is a single isotropic peak, even without any spinning. And you can confirm that this is indeed the isotropic peak because you can actually spin this rotor and then look at this. Of course, if you now change the orientation of these glass plates to something different, you'll get a completely different orientation. And so you can see that this peak that you get over here is no longer the isotropic peak, but it's something at the edge of the spectrum. So it's something like 20 ppm over here. So this is a very, very interesting case. In fact, you can get very high resolution for even protons in these systems, because the rotational diffusion is of the order of 50-60 kilohertz, which would correspond to magic angle spinning of the same frequency. So if you spin samples at 50 to 60 kilohertz, you generally get very good resolution, and this is actually what they see over here. So we'll come back to this this particular experiment at the very end, when we'll talk about some aspects of this rotational diffusion and in the context of measuring these couplings and magic angles. But in all of these cases, whatever I've talked about right now, there's no magic angle spinning, so you're sort of restricted to either studying one site or maybe studying multiple sites at a time, but taking an average view of what's. But if you really want a site-specific resolution, then magic angle spinning is really, really necessary. And the way we describe the magic angle spinning experiment is to try and understand how these tensors again change as a function of the spinning frequency, as a function of the angle to which the rotor is kept. And the simplest way to do this is by looking at them as spherical tensors. So this A part of the Hamiltonian is the spatial part. The T part over here is the spin part. And the way we describe the system is going from the principal axis system to the molecular fixed frame, to the rotor fixed frame, and finally to the laboratory frame where you also have the magic angle spinning. So this theta m over here would refer to the magic angle spin, to the transformation to the magic angle. So all of the tensors, all of the rank 2 tensors that we saw, CSA, the dipolar coupling and the quadrupolar coupling, can be described by this method. For the simplistic, for simple reason, but we are going to discuss quite a bit about the heteronuclear dipolar coupling. What I will just show how the heteronuclear dipolar coupling itself looks like. So since this is all spatial rotations, the spin part, this T part, is not touched. So you just have this 2 Iz as Z, which is your heteronuclear dipolar coupling Hamiltonian, remain as it is. And then you have a time-dependent term in your Hamiltonian, which has just one frequency modulation, that is the magic angle spinning. So e to the I m omega t is the term that describes the spinning of the sample as a function of the time. And this term omega dm picks up components from all of these axis transformations and is given by these terms over here. So let's look at these terms a bit more carefully again. So what you have is sum from m-2 to +2, and this omega d depends on m, and also there's m over here that gets picked up to the magic angle. So for m is equal to 0, this d2 to 0 minus theta m, this term is set to 0. I mean, once we set theta m is equal to 0, is equal to 54.7 degrees, that immediately sets the t to 0, 0 of the theta m term to 0. That's just 3 cosine square theta minus 1 by 2. That's how we get the magic. So for this m equal to 0 term, just completely drops out from this equation. So all you have to worry about is the m equal to +-1 and the +-2 term. And irrespective of what this number, so it's this part is just going to be a number over here. But you'll notice is that this is e raised to I m omega rt. So e raised to I +-1 omega rt is just cosine of omega rt. And for m equal to +-2 is just cosine of 2 omega rt. So you see that both of these terms oscillate with a mean of 0. So if you look at the instantaneous instantaneous value of this Hamilton as a function of how you're spinning, you'll see that this goes up and down and up and down. And if you're doing this fast enough, you're allowed to take an average over an entire rotor from 0 to 1 over here. That's what the average Hamiltonian theory tells us. And so once we do that, this goes to 0. So A, B, C, all the 3 terms go to 0. And this is true for any interaction that we want to measure. So this is how the interactions completely go to 0 under magic angle spinning. But we are interested in measuring these interactions, right? So if you want to measure these interactions, then we need to somehow interfere with this averaging due to MAS, and that's where the recoupling techniques come into picture. So the very first recoupling techniques, both dip shift and radar, use pi pulses for recoupling. So instead of allowing this instantaneous Hamiltonian to just evolve over time, what we do is place pi pulses at, in this case, a quarter tau hour and 0.75 tau hour. So within a rotor period, you have 2 pi pulses. And what that changes is the instantaneous direction in which the Hamiltonian evolves. Now imagine you have lots of pi pulses. So this A block is much longer than what is shown over here. And this B block is also much longer than shown over here. Then it's only the central part over here where no recoupling happens, but the average from 0 to 1 over here is no longer 0, is some value. And the average from 3 to 4 over here is also some value. So that means that your whatever is the interaction that you're looking at, in this case, the dipolar coupling, is not averaged to 0 over this entire rotor period, and that's what recoupling does. So the first thing that we need to do is try and understand how much of your dipolar coupling have you recoupled back, because depending on where you place the pulses or what kind of sequence you use over here, you're going to change the amount of the dipolar coupling that is recoupled back over here. But before that, before going to that, we must first try and see for our particular case what is the interaction that might be the most important. For example, you have two options. Of course, quadrupolar couplings are there, but either you want to deuterate your sample or maybe O17 label your sample, and then those experiments might be relevant. But if you're just worried about C13, N15, and proton, then it's only dipole-dipole coupling and the chemical shift anisotropy. These are the two things that you would want to mention. The dipole-dipole coupling is simpler. The tensor is symmetric. Only the anisotropy is important over here. The tensor anisotropy depends on only one parameter, which is the distance between the two nuclei. So it goes as the inverse cube of the distance between the two nuclei. And for cases where distance is known, you know what the exact value of the tensor is. So for example, if you look at one bond couplings or certain two bond couplings, then you know exactly what the absolute rigid limit value of your dipole-dipole coupling is going to be. Chemical shift anisotropy, again, is not as bad as I make it sound over here, but it does have a problem that the tensor is not symmetric. You have to consider both anisotropy and asymmetry. So instead of just one parameter, you already have two parameters. The CSA does vary from site to site, especially in proteins. So you sort of need to use an average value, or you need to know exactly what the value of that particular site is. The rigid value, the rigid limit value for that site is. And in general, we do not also know the exact tensor orientation, although if you're just working with protein samples, then the approximate tensor orientations are also known. So these are not very, I should say, if you're just working with protein samples, these are not very tricky problems. If you're working with something much more different and something that's not been studied in detail previously, then maybe you need to consider carefully whether you want to use the CSA. Dipole-dipole coupling, again, irrespective of the samples that you use, you should always be able to. So then going back to our experiment, which is this readout experiment. So when we talked about having these two pi pulses per rotor period, this is exactly what we do in the readout experiment. And the way the experiment is done is that you have your magnetization on your spin I. And I've shown over here a 90-degree pulse to generate the magnetization, but it can be pretty much anything. It can be inept, it can be CP, it can be DNP, it can be any method that you want to use to generate magnetization on your I spin, and you just have a simple echo on that. Okay, so if you do not have any pulses on your S nucleus, then this is just undergoing magic angle spinning. So what you will see is the sympathy to prime decay in this case. However, if you recouple the heteronuclear couplings between S and I spins, then you are going to have some. So in your Hamiltonian is not going to be just zero. It's going to be some effective Hamiltonian that is going to be a dipolar Hamiltonian. So you have this IZSZ term over here, and then if you place these pulses exactly like it is shown in this diagram, where you have the pulses at a quarter tower and three-quarter tower, and then you have the central pi pulse on the S spin as well, then you can very quickly calculate what the effective Hamiltonian for this readout is. Now, this term in the brackets over here just depends on the length of this pulse. So we just ignore this for a moment. But there are a few others over here. So these are just 2 root 2 is just a simple factor. And delta D is now the strength of the dipolar coupling that you use. Cos gamma and so gamma and beta are the crystallite orientation angles that you use, and then IZSZ has the spin terms. So this looks almost exactly like if you consider that this entire factor over here is just a constant for a particular orientation, then this looks exactly like your for example, the heteronuclear J coupling that you use in solution in NMR for inept transfers. And in fact, this experiment looks exactly like inept experiment. For example, if you had just J couplings, then pi pulse 180, 180, and then you'll have an anti-phase migration at the end of the day over here. So the only difference in magic angle spinning is that if you don't apply these pulses, there is no heteronuclear coupling. So there is no evolution of the heteronuclear dipolar Hamiltonian. But you apply these pulses, and then Hamiltonian looks exactly like your heteronuclear J coupling or heteronuclear dipolar coupling. And at the end of the day, you should also expect on the S, if you put a pi and pi pulse over here, an antiphase term that you can then detect. However, we don't do that. We just have your magnetization on I spin. You can transfer the magnetization, and this is an experiment called TIFR, where you can use where you can transfer the magnetization from the I spin to the S spin using this method. But normally what we are just looking at the evolution of this I spin under the effect of this Hamiltonian. So how do you do that? So if you know a bit of Python, then you can very quickly simulate what it should look like. For example, if you have a Hamiltonian edge, then the signal, when we are starting with an IX magnetization and detecting, let's say, I rho, or I plus or I minus, then the signal will go something like this. It will be just a cosine of whatever is this Hamiltonian over here times t. Our Hamiltonian is some constant times the dipolar couplings times some factor over here which deals with the orientation of the. So if you have a simple single crystal, what you will see is a pure cosine term, and of course you're going to see some decay. So the actual signal is going to be a decaying cosinusoid. Normally we do a control experiment where we just get this decay and not get this oscillating term, and so what we will get a signal that's compensated for relaxation, which is going to be just a pure cosinusoid. But of course, in most of solid-state NMR, you're not going to be dealing with a single orientation. You're going to have all possible orientations. So you need to sum over the gamma and the beta angles with appropriate weighting factors. And what we'll see is that now what you have is a sum. Your signal is going to be a sum of all of the signals with different frequencies. And this is what this blue curve is. So if you sum up all different frequencies in your powder, you'll get this blue curve. And by convention, you can either plot this as, you can just plot this as S by S naught. That's what this curve is. S naught is your control and S is your actual signal. Control is just your spinning core. Or you can plot the delta S. So that's 1 minus this, which is just going to be the reflected around 0.5. So this is your readout curve. And now the nice thing about this is that it just has one variable. In fact, you don't need to make it so complicated over here. There's a closed form analytical solution to this equation, to this integral. This is a Bessel function, of the second kind, and so you can. There's an analytical form which you can use to actually fit your data. Again, the simple. If you get a curve, if you look at how your dipolar coupling, how your signal is evolving as a function of time, you should get exactly these curves. So the way we actually measure these things in complicated protein samples is by first recording a multidimensional experiment. So you can have, in this case, this is a TAR experiment, or you can have, if you're spinning fast, you can maybe have a simple NH correlation or a CH correlation, and then you can look at these peaks in a pseudo dimension, in a third dimension or a fourth dimension, depending on what your multidimensional experiment is. You can evolve the dipolar coupling, and if you evolve the dipolar coupling, then the intensity of this peak is going to be changing as a function of time. If you now plot this intensity, in fact, in this case, it's delta S by S that I'm plotting over here, you will see that you will get this nice curve over here, which you can then fit to a dipolar coupling, and that's how you extract a dipolar coupling. Now, this remains exactly the same for either dipolar coupling or the CC. So how do you tell whether your sample is dynamic? So in the rigid limit, for example, you can have a dipolar coupling that oscillates like this. However, once you introduce motion, for example, if you have a symmetric three-side motion, you'll see that in the limit of fast exchange, you get this very scaled value. So this curve, you'll see that it's oscillating a bit of, it's rising a bit fast, reaching the value of 1 kind of fast, and then oscillating at these values, while this value will fit to a lower value of dipolar coupling. Will fit to a lower value of dipolar coupling. The same is the case with, for example, two-side exchange, except that you'll get a coupling that is slower, but you will not recover this exact nice oscillations at the end over here. So we define this order parameter as the one that you measured. For example, if you are in this regime, then you would measure this dipolar coupling, which is going to be lower than the theoretical one, which is the rigid limit. And then you define the order parameter as the measured value divided by the theory value. And this is, of course, only true. You can define this order parameter only when you have really are going into a fast exchange. And under this condition, this exactly corresponds to the same order parameter that comes from, for example, the Lipari-Szabo models in solution. So how do you know that? So you can actually use this to determine dynamic residues. This has been done by quite a few people over the years. I'm just highlighting a couple of different examples. For example, this is recent work from Paul Chanda's group, where is looking at I forget what protein this is, but a couple of different residues in this protein have a very low order parameter, which means that you expect the dipolar coupling to be, in this case, this is NH, sorry, CH that they're looking for. So you'd expect them to be around 21 to 22 kilohertz, but you're seeing dipolar couplings of the order of with the order parameter of 0.2. So that's about 4 kilohertz instead of 20 kilohertz. Immediately that tells you that these particular residues are, there is something different going on with these residues, maybe with this residue as well, where these residues are actually dynamic. You can interpret this, the square of the order parameter as, again, from the relation that we saw earlier in terms of the diffusion in the cone model, but maybe it's not really diffusion in the cone model. You can also, if you know a bit more about what is happening in the system, you can interpret this in terms of different models that are going on. If you really compare, if you look at, for example, one nice thing again the Shanda lab has done is look at the order parameters that you get for crystalline solids with the same protein studying in solution NMR, and then there is a different correlation over here. So you see that the order parameters do at least follow the trend of what you get in solution NMR, except that this is a direct measurement of the dipolar coupling and not something based on the relaxation. There's one interesting way in which you can also interpret dynamics is this very interesting case of a protein in solids, where what these researchers observed is that instead of the entire curve going all the way up to 1, it just goes all the way up to like 0.6 or 0.7, and you get an oscillation around this value. Now, this can only happen, assuming everything is done perfectly fine. The only way this can happen is that if you have a part of a protein sample that's completely mobile, does not contribute to the radar dephasing, but you still see the signal, whereas about 70% of a protein is rigid. So you can already tell whether there is some kind of mobile component to your crystal, in this case, as much as 30%. You can do many more complicated things. For example, you can look at aromatic ring flips, dynamics in this in the systems where you can label specifically the aromatic groups. For example, you can label the meta positions, where if the ring flips, then you're going to have a change in the conformation from this side to this side, and this is what you can sort of detect by looking at the order parameter as well as, so you can fit a two-site exchange model to this and come up with ways, come up with an understanding of the conditions under which some of these aromatic residues which are involved in packing of some of these amyloid light aggregates can actually flip. And depending on the crystal forms over here, this is what the study does. Depending on what the crystal form, you can have different packings in the crystal, and that will encourage different amounts of flipping in different crystalline forms. So hopefully by now you're convinced that you really can do quite a lot by just looking at the dipolar coupling and just measuring this one parameter of the dipolar coupling. But let's look at the experiment in detail, the radar experiment in detail, and see whether we can really use this experiment for a completely large number of cases. So the one problem that often people face is try and measure the carbon to proton dipolar coupling, which is going to be of the order of 22 kilohertz. This is the one-bond coupling, or in the case of CH2, it's maybe slightly stronger because you have two carbons that are connected. You have to consider the average of those. In this case, what happens is that because you need to wait for one entire rotor period for the evolution, so you cannot just collect a point in between over here. So you need to wait for multiple rotor periods in order to collect a point. What ends up happening is that the curve actually is supposed to look like this, but you end up collecting only like these 3 points, and that is very difficult to fit anything to this. So you need to sort of scale down the coupling here. So you can use this technique called shifted radar, where, for example, again, you're looking at the gamma dependence of this coupling. So it's just a cosine of gamma function over here, and different gamma crystallites at different gamma notation will be recoupled to a different value in this case. And what you're going to see is the sum of all of this. Now, in the case of shifted radar, you'll see that each gamma angle is coupled slightly differently. In fact, you have the m equal to plus minus 2 terms as well. But the overall magnitude of the tensor that is recoupled, which is proportional to the this shaded rectangle that I've drawn over here, is going to be slightly lesser. And when you do that, you're going to get some scaling over here. So you lose these very nice oscillations because you're mixing of many different components over here. But at least you will not get just 1 or 2 points on this curve. You'll get several points on this curve. And that's very, at least the initial part you can fit. So this is the standard way to do it. But as you spin faster and faster, you realize that you cannot really shift this pulse anymore, because if you spin fast, then you really have a very small rotor period in which to put these two pulses. And if you shift one of them, then this one is going to clash with the previous one. So you need to make a sharper and sharper pulse. And of course, you also have this trouble with these non-ideal oscillations over here. So one way to try and do this is to use the fact that readout itself is a non-gamma encoded sequence, which means that the recoupled Hamiltonian really depends on where you start in your rotor period. So for example, if you start slightly differently, so for example, this A block and the B block is where the readout is happening. These two blocks must constructively recouple with each other in order to give you complete recoupling. However, if you start A slightly earlier and you start B slightly later, what you will see is that your gamma dependence for this block and this block are completely different. They do not constructively add up. In fact, they add up to only partially. So your strength of the dipole coupling is slightly lower, but at least there is no recoupling of any of the other terms, m equal to 2 term. And also the distance between these two pi pulses always remains exactly equal to half a rotor period. So there is no additional RF requirements over here. If you do analysis of the effective Hamiltonian for radar, you will see that this looks exactly like the radar Hamiltonian, except you have this sine 2 pi epsilon term. This epsilon depends on how much you shift this A and the B block with respect to this center. So this is sort of under your control. And you can go all the way from a recoupling factor sine 2 pi epsilon of 1 all the way to very, very low recoupling factors depending on what you want. And then when you do the experiment in this case, you will get these nice oscillations as well as you will get that initial nice initial build up. So this is one way to utilize the fact that readout is a non-gamma encoded sequence, and you can really play around with the position of these pulses to get the recoupling strength that you sort of want. The experiment that is sort of very, very similar to readout is the dip shift experiment, where you the traditional way in which this experiment was always done is that you evolve just the heteronuclear coupling for a small amount of time, and then you just turn off the heteronuclear coupling and you increase this T1 time over here, and you simply go on the spin that you're detecting. So this is a constant time experiment, whereas readout, you're increasing the number of pulses that you're plotting over here. You'll get curves that look like this. So for example, if you have a complete echo, so if you have a complete, if you have just zero recoupling time over here, the normalized intensity is going to be very high because you have heteronuclear decoupling for a complete period over here. But if you now increase this quite a bit, you will actually end up getting complete dephasing because your time is long enough that your entire sequence has, entire spin has dephased. We can sort of combine the readout and the dip shift experiment into a single experiment and sort of try and analyze these two experiments as a part of a single experimental block, where we see that, okay, in the readout experiment, we can tune how much of the dipolar coupling we recouple and then change the number of the time for which we apply the recoupling pulses, which is what this is. So if you change the n over here, the number of recoupling pulses, you will get curves that look like readout dephasing profiles. And these are different scaling factors. So different values of this are tau naught. However, if you keep the n constant while change tau naught, you'll get exactly the dip shift profiles. Okay, so both of these experiments, again, readout and dip shift, although they are used for different cases and we call them different, there are many different implementations of them. But in general, you can really analyze them in a very simple one pulse sequence, and then that simplifies really at least your understanding of how and when you can apply these sequences. So in general, readout is applied when you have weak dipolar couplings. So you can really go to, you don't really know how long you need to evolve in order to do this to get a reasonable dephasing curve. Dip shift is generally applied for NH or CH, very strong dipolar couplings, where you can then really scale the dipolar couplings You really need a short, constant time evolution in order to evolve them. But if your dip is much smaller, then you can say something about what the dipolar coupling is. And again, both of these curves can be fitted to a single. Again, so these all the experiments that I talked about have been used quite a bit for determining distances and dynamics in systems. But one place where they have not really been applicable so far have been at very fast magic angle spinning conditions when you have fully protonated samples. Okay, so or non-deuterated samples. So that is because the one drawback of a radar experiment is that it really cannot deal with homonuclear couplings. So, for example, if you have very strong homonuclear couplings on the protons, and if you put these pi pulses on the proton, then what you're going to get is very, very strong deviations from the ideal diffusing profiles. So ideal diffusing profiles are supposed to go all the way up to 1 and then show some clean oscillations over here. But what you will see is that if your RF amplitude is kind of small compared to your spinning frequency, then you're not going to be able to get radar diffusing profiles that go all the way up to 1 and then oscillate, which again, these are spin system dependent deviations. The x-axis over here is sort of a modified x-axis where we're sort of taking into account all the effects of the strength of the coupling, any of the scaling factors, spinning frequency, all of them. So it's just a unitless number over here. So any change, anything that does not reach all the way up to 1 over here is a spin system dependent deviations. And in general, while determining dynamics, you want to avoid any spin system dependent deviations because you probably do not know much about your spin system to begin with. You do not know really how dense are the protons around it. So you can see that if you really go to maybe 300 kilohertz RF amplitude, so when you're spinning at 100 kilohertz, so all of these simulations that are at 100 kilohertz magic angle spinning, then you can maybe recover your profiles. But 350 or 400 kilohertz is too high RF field, even if you're pulsing on the proton for a short time. So that's not quite feasible. And the more important factor is that if your dipolar coupling is actually low, so instead of 25 kilohertz, which one you detect for CH, it's something like 5 kilohertz, then these deviations are even stronger. And so the very cases that you want to study, which is the scaled autoparameter, is the same ones that will give you all sorts of troubles. There is one solution. There's a sequence called SR412. I think I have a reference in one of the later slides, which you can use over here. And this is interesting, but it has its own problems, which we will talk about. What we have found is that instead of just pulsing on nitrogen, on proton, you can pulse on your X nucleus, which can be the carbon and nitrogen. And in this case, if you're spinning very fast, then this echo times are long enough that you can really record these couplings, and there is no very low nitrogen dipolar couplings, so these pulses can actually be very long, and then you will really get ideal radar diffusing profiles, even if your power levels are very, very low or your coupling strength is also very low. So you sort of avoid these high RF amplitude requirements, and the echo is on the proton, so your signal decay is a bit faster, but really at 100 kilohertz, even with fully protonated samples, this is not a big issue. Of course, when your pulses are on a nuclear like nitrogen, even this pulsing, if you spin very fast, then this pulse amplitude that you require is still going to be very, very large. So, so for example, if you're spinning at 100 kilohertz, you need to put 100 kilohertz pulse over here, which is not that nice for nitrogen. So, what we have is a sequence called T-dot, where instead of pulsing twice every rotor period, you pulse twice every 3 rotor periods. And what that allows you to do is extend your pi pulses beyond the rotor period. And again, this sequence works exactly like that of radar, except again, you have a scaling factor that comes because of the longer echo, as well as this longer pulse length, which is now going to be incorporated in these factors. But the RF requirements are quite low. And so now instead of using the scaling factor, you can use the scaling factor of the pulse, where you can both scale the sequence so that you can get all of these nice diffusing profiles, and you can also use low RF frequencies for nitrogen. So that kind of works very, very So the only thing that you need to really consider while doing these experiments is that how are you generating this magnetization. So for example, I said previously that you can pretty much use any method to generate your magnetization, but that is not quite true. If you use, for example, CP, then CP itself is crystallite dependent. So you're going to see effects on your radar rephasing profile that are because your CP has already selected out some fraction of your crystallite orientation. So again, a bit of Python code. Instead of doing a simple radar averaging over the entire rotor, you need to now have an additional factor which you kind of don't know, which will again cause deviations in your radar rephasing profile. The only solution I have at this moment for this is to just do a brute force calculations where you vary the parameters of cross polarization itself in order to fit your data. And that actually works quite well. You can do this for small proteins. So this is GB1 spinning at 100 kilohertz, and you can collect both the CH and the NH data quite cleanly. You can get site-specific information about dynamics, and you can get, in this case, GB1 is fairly rigid, so there's only one residue over here, which is kind of dynamic. Rest of the residues are kind of flat, but the dephasing profiles are very, very clean. And even at 100 kilohertz for a polyproteinated samples, you can really do these measurements. There are other methods. Of course, I focus on radar because it's the most often used technique for good reason. But there are other ways in which you can, again, measure the dipole coupling. So in fact, you can use cross polarization itself to use dipole coupling. And this nice comparison between radar and this cross polarization method in order to measure the couplings. You have several symmetry-based sequences. This is SR412 is very, very nice method, especially if you're trying to measure couplings between proton and a quadrupolar nuclear, where you can't really pulse on the quadrupolar nuclear, so you have to pulse on the proton. So SR412 achieves heteronuclear decoupling, but also homonuclear decoupling. So this is a nice way in which you can do that. There's some very nice experiments at slightly 40 kilohertz sort of spinning speeds from the Polinova lab, as well as Josef Lewandowski has several R symmetry-based sequences that can be used on deuterated samples at very fast spinning frequencies. There is also an off magic angle spinning. So instead of sitting at exactly the magic angle, you can detune your angle slightly and then look at how. So if your angle is detuned a bit, you can the oscillations for your J coupling in this case are going to be contaminated with some residual dipolar coupling, and that is what you measure in this case. With deliberate setting of the angle. This is a method that was developed by Malcolm David several years ago and has been used recently with in combination with proton detection by Burnrife and others. But radar still remains one of the methods that is very, very robust to experimental imperfections. And one thing that you need to always consider, especially with the symmetry-based sequences, is to see whether they're really robust to RF inhomogeneity or not. So radar itself is extremely impervious almost to RF inhomogeneity, and the XY8 phase cycle that you use is also robust to pulse errors. This combined with the very high scaling factor. In fact, radar has the highest scaling factor of all of the known sequences. So the very high scaling factor, what it does is you can really measure very, very small type of couplings as well. There is this nice paper from some years ago now from Matthias Ernst, where they looked at several different sequences and how are they robust with respect to several different parameters. And I think this is a good place to start if you want to compare your method to radar. Right, so that is about radar. And again, most of the interpretation that we saw was based on an order parameter. But there's a different class of experiments called the codex experiment, which also uses this gamma encoded, the non-gamma encoded nature of radar in order to recouple experiments. So again, the experiment is very, very simple. You have this version of radar where the only thing that is missing is this pi pulse on the S channel. If you don't apply these pi pulse, what happens is that you get a perfectly zero scaling factor. So even though you're applying these recoupling pulses, the recoupling in this part completely cancels out the coupling in this part, and you get perfect echo over here. So nothing should happen if you just. What the codex experiment does is splits it up further. So you have a 90-degree pulse where now you store the magnetization along Z, and you have 90-degree pulse which brings it back. So if nothing happens during this period over here, then this works exactly like as before, and you will see a complete echo back over here. However, if something happens during this pulse sequence, for example, if you have some CSA tensor or your dipolar tensor that rotates, that changes orientation, then the evolution in the initial block is not going to be the same as the evolution in the second block. Okay, and you're not going to get a perfect echo. In fact, your amplitude of the signal that is recovered at the end is going to be decreasing. So, of course, there are several things that need to be taken care of. For example, this recoupling time over here needs to be perfectly synchronized with the MAS, and most of the modern hardware allows you to do that with triggering with a triggering cable, with triggering signal for the MAS. There's also compensatory delay. So whatever time you are using over here, there's a compensatory delay that you need to sort of use. So what this experiment is, and of course, the only process that's happening on in this scale is just the T1. So you're sort of limited only by the T1. So if your T1s are like minutes, then you can keep the mixing time of several tens of seconds, and even then you should be able to detect very, very slow exchange between these sites. And this has been done quite thoroughly by several groups. And here's a simple example of the small molecule called dimethyl sulfone, where people have looked at how this molecules, even in the solid state, it rotates. So what you can do either is that you can change either the number of recoupling blocks over here, or you can change this mixing time. If you change the mixing time, and if you have a correlation time that is different, you're going to see different decays. You can fit this to a simple exponential curve, and then you should be able to get the decay profile. You will see also that this reaches up to something like 0.5, which already tells you that this is a two-side jump. If it was a three-side jump, then this would probably go all the way down to 0.3. If it was a four-side jump, then this curve will go all the way down to 0.25. So not only it's going to tell you what the time scale of motion is, but what the motion actually is. And again, if you now change the recoupling duration, what you're going to see is that depending on how much is this angle change, you're going to get a different decaying profile as a function of the centaur. So it's going to be very, very powerful to look at different things. However, a word of caution, there are several things that can go wrong with this experiment if you're not careful. For example, in N15 CSA codex, depending on what you detect, a cosine component or a sine component, you're going to get very different curves, and only this is the real dynamics, or this is not really real dynamics. The dipolar codex experiment especially is prone to contamination quite a bit from the rider effect. And so if you do want to use this codex experiments, especially for studying proteins in deuterated samples, this particular paper from Kaustubh and Kushelnitsky is a must read. And the rider effect, of course, is what the rider effect relies on is that we sort of say that nothing happens in this mixing time, but there are several things happening in this mixing time, and the one thing is either spin diffusion, so spin flips, or simple T1 relaxation if this time is too long. So you're going to get an effect on your recoupling because you're going to have other processes, relaxation processes happening either during this mixing time or this evolution time. Good. So that's about the codex experiment. So the last thing, couple of slides that I want to talk about is I want to sort of go back to this rotational diffusion of membrane proteins. So we saw that you have this rotational diffusion that is happening for membrane proteins, and again, the time scale for this rotational diffusion for single transmembrane releases and also transmembrane release bundles is quite fast. Much faster than the strength of the inverse of the strength of the CH and the NH dipolar couplings, and definitely the CSA. So we should be able to detect this kind of a motion, this rotational diffusion, by using simple measurements of the CH and the NH dipolar couplings. So here's a case from Mehong's lab several years ago now, where you're looking at a simple CD3 group in two different lipid membranes. And you can see that depending on what the temperature is, so if you have either a completely frozen sample, where you should not expect too much motion at 243 Kelvin, you get the dipolar pattern that looks kind of broad, whereas the pattern is substantially narrow at these high temperatures where there is this uniform rotational diffusion. Now, The reason why this rotational diffusion is important is that you can use this to map changes in the transmembrane helix orientation, either due to changes in the environment. For example, if your bilayer thickness changes for some reason and that causes the transmembrane helix orientation to change, or in the course of the natural transport cycle of your transporter, you are going to have some changes in the transmembrane helix orientations, which you want to detect. So how do you do that? So for example, let's consider a simple alpha helix, which is rotationally, which is diffusing, which is undergoing rotational diffusion with your NH, if the tilt of this helix is exactly the same as the bilayer normal, so it's the tilt angle is completely zero, then all the NH bond vectors are going to be pointing in the same direction. And you see there is no rotational diffusion. So there's no diffusion in sort of a cone that is happening over here. So when you measure the dipolar coupling, it's going to be every single NH bond vector is going to have exactly the same dipolar coupling, which is about 11 kilohertz. However, when you have a tilted helix, you look at this particular NH bond vector is going to execute a large rotational diffusion, which is going to be this cone is sort of going to be much bigger than this particular cone. So you're going to have a much smaller scale of rotational diffusion that's happening for this one rather than this one, and it's going to get reflected in the dipolar coupling that you actually measure. So you're going to get, for example, you're going to get this oscillating patterns, which now don't reflect anything about the dipolar coupling, but it indicates something about what your helicity is. So you're going to get these helical patterns, these oscillatory patterns that you can fit to exactly the transmembrane helix orientation. And this has been used quite extensively by several groups now to either look at protein structures themselves. For example, this is an example from a protein called MRFT from the group of Stanopella, where they were able to measure both the NH and the CH, the NH, in this case, the NH dipolar couplings for 2 stretches. And once you know what the transmembrane helix orientation is, you should have no difficulty in actually solving the structures combined with all other data that you have on these proteins. You will get the relative orientations between these helix exactly correct. It's also, again, extensively used by the group of Mehong to look at how the transmembrane helix changes orientation under different conditions. For example, at a high pH, the tilt angle is kind of small, and then you have have a helix which is much more shallower. Whereas at a low pH, where the tilt angle is much larger, so you get a much larger oscillation in the case of this M2 channel. All right, so I think that brings us to the end of this talk, and I hope I convinced you that these anisotropic interactions can be measured directly and have important effects on and dynamics has really nice effects on these anisotropic interactions, which when you measure tell you something about directly something about what kind of motion dynamics is going on in solids. The take-home points are that some of these techniques, especially the Reed-Orr technique, the heteronuclear dipole coupling, are very well established, well understood, especially where they fail and what things you must keep in mind when you perform these experiments. And at the end, some of the last bastions remaining of where this experiments can be applied, especially fast MAS frequencies and fully protonate samples. These are also now possible. So you should find the pulse sequences for actually executing these sequences, and also simulation codes for Simpson, especially at my GitHub, or you can find them from several other people. But if you go to this site, then you should be able to find these simulation codes that you can play around with for different versions of Reed-Orr, different conditions, and should be able to see for yourself that these experiments actually work. And these are also useful in actually fitting your data once you have them. Right. So that brings us to the end of the talk. Again, we have some work, especially in this epsilon Reed-Orr and the Reed-Orr one, which has been done by several people in collaboration with my colleagues over here at TIFR, Madhu and Vipin, as well as together with Matthias Ernst at ETH. Most of the people over here are involved in studying protein dynamics, and the reason we are interested in all of these methods is because we want to use them for studying all these protein dynamics. We have a nice NMR facility over here where we can do all of these nice experiments, and funded by mainly TIFR Hyderabad at the Department of Atomic Energy and some funding from the Department of Science and Technology of India as well. All right, so I'm done, and I will be happy to take questions from any of you there.
Thank you so much. That was a really excellent talk. So everyone, please put your questions into the Q&A. I see we already have one, but while people mull over what they're going to ask, I'll sneak in with a quick one. So I think I kind of have an answer to this myself, and or think of it as maybe a silly question, but near the beginning you mentioned that one of the fundamental assumptions of working with dynamics is that we're assuming that the change in intensity that we see in the spectrum is due to the fact that the orientation is changing, but the magnitude of the interaction is not. And it seems like a very safe assumption, and for the most part,
yes.
But are there situations where we do need to go back and rethink that assumption at times, or does that ultimately have a rather minor impact if there is, say, some coupling between orientation and some other thing like the bond length?
Right. Yeah, so that is always something that you worry about, and that's why I always like dipolar couplings, because there is less chance of that happening, although it's not a zero chance that happens. For example, if you have the NH amides, they can be either involved in a hydrogen bond or not involved in a hydrogen bond. You're going to have a small change to the length of the NH bond, and that's going to reflect what you consider your rigid value limit to be. But if you're looking at, for example, CH or the methyl group, then there is practically no way you can have a very long, much longer, or at least the differences are tiny enough that you should not be really having a rigid value limit that's completely different. NHs, again, yeah, are tricky. So you don't know really when you have a slightly longer bond. But in that case, in the NHS case, you could also sort of look at a yes or no answer instead of interpreting it as a real order parameter with a value of, let's say, 0.51 or something like that. I don't think that degree of accuracy is justified for something like NH. But if you have a 0.5 order parameter, that already tells you something about that it's not going to be, the bond lengths are not going to be really large. So if you have anything above 0.9, let's say, I wouldn't interpret it as a change, especially for NH. But if you have something that is like 0.6 or something like 0.2, then that immediately indicates that that's a real dynamic effect that's going on over here. But yes, you do need to consider that. For the CSA, this is, of course, a problem that you don't know whether your CSA has completely changed its magnitude or not. Although the strength of the CSA, again, changing by a huge amount is not, I mean, it will not suddenly go to half its value, because at the end of the day, you're still dealing with an amide group, or you're still dealing with the C alpha group, or still dealing with the methyl group. So it doesn't change by, change by a factor of half. It will be a 10% effect, but the 10% effect, you sort of need to keep it at the back of the mind. If you really rely on that 10% effect, then I think the only way to really be sure that you're looking at dynamic effect is to completely freeze the sample and then again measure it, which is what normally people do. Completely freeze the sample and see that the dynamics is completely quenched. Where you now unfreeze the sample, then you sort of get back your dynamics.
Great. Thank you. So our first question from Zhao, saying the high power proton decoupling during a long redoor nitrogen carbon recoupling block would cause heating problems. So what proton decoupling methods would be feasible to use during this nitrogen carbon recoupling block?
Right. So if you're measuring the nitrogen proton and the or the carbon proton dipolar couplings, then of course you cannot decouple. So in that case, there is no decoupling. This is important when you do CN redoor. So if you're doing carbon nitrogen redoor, then you have to use decoupling on the protons. And typically, if you see what the evolution time that you would use for your CN dipolar coupling evolution, so that coupling is of the order of a kilohertz. Which means that your entire, let me go back to a place where I have a reader dephasing profile. Yeah, this is the CN case actually. So if you're measuring, well, this is not a good way because this is the deco. Let me again try and find, yeah, this isn't okay. So again, in this case, this would correspond to a CN coupling of about kilohertz, which means that in order to get this entire dephasing profile, you need about 5 milliseconds. And really the important part is this initial part over here. So I would say about 3 milliseconds of decoupling is what you need to that. Now, this is much shorter than what you need for the evolution of the chemical shifts, which can be of the order of 10 to 15 milliseconds, or maybe even longer when you do that. So, especially when you are spinning slow, yes, there is a significant. I mean, there's about a 2 to 3 milliseconds of retronuclear decoupling that you need to use in order to do this. But it's not that long. It's not tens of milliseconds. Of course, the longer the distance that you want to measure and the weaker your dipolar coupling, the longer you will need to apply your decoupling. And of course, then you need to carefully see whether you really need that much of an evolution in order to do that. So the type of decoupling that we use. So now, again, there are some aspects of this that we discuss in one of the papers, but especially when you're spinning slow, I think what you do is you just use the decoupling scheme that you are normally using in your direct dimension as well. So either a spinal or TPPM or sweep TPPM, RCW decoupling, you use exactly the same ones when you're evolving your redoor dephasing profile. But remember that there might be interference with the decoupling scheme and your redoor decoupling. So that somehow you need to avoid by keeping the decoupling power very, very high. This normally is not a problem when you spin a bit fast, because then you can use low power decoupling schemes, and then you are in a completely different regime for your synchronous recoupling for your redoor and your asynchronous recoupling for your heteronuclear decoupling. But again, most of the time the CN coupling is not used just because it's much weaker. Most of the time, when people talk about dynamics, you're really looking at either the NH or the CH dipolar couplings, where, of course, you do not need to use decoupling.
Great, thank you. All right, our next question is from Fred Peras. It's been shown that the chemical shift scaling experiments can be used to tune the coalescence point and emulate VT experiments. Does a similar principle apply to the dipolar scaling methods? Or in other words, near the intermediate exchange limit, will the redoor dephasing rate be a linear function of the scaling factor? Or is there some crossover when it moves from slow to fast exchange without changing the temperature?
Right. So it is. In fact, this is exactly correct. In fact, if you think about it, if you just had if you didn't have a powder, if you had a single orientation, what you will see is a chemical shift. It's just a cosine, right? Cosine or sine, some sinusoid. So, and then if you look at that sinusoid, if you look at a single orientation and how that changes, how the evolution of that signal changes when you have an intermediate time scale motion, you will see that same exact dampening effect that you see. Except now, when you look at the chemical shift, you're comparing chemical shift in two different cases. What you're looking at over here is a single sort of a dipolar coupling. So your oscillation is a single dipolar coupling. So you're almost sort of looking at motion between either a zero frequency and a dipolar coupling frequency, or if you have, if you know what the dipolar couplings in the two limits are, if you have, for example, a bond that is changing, then you're looking at, in that case, the difference between two dipolar couplings. But it is exactly the same as what you would expect in this dampening that you expect in the Bloch-Mokano regime. However, because you're always looking at the powder pattern, it is not very obvious how to actually fit these curves over here. So, for example, in this rigid limit, you have these nice oscillations. In the fast exchange, you have these nice oscillations, but you have this flattening over here. You could do something like doing a redoor transform and then try to map this as in the frequency space rather than in them, and then you will see a very broad peak over here. But it's, I mean, the signal to noise is such that it's not like a chemical shift. I mean, these are really single points that are collected with error bars over here. So it would be kind of difficult to get to this point. There is one thing that I will point out though, that because we can tune what the dipolar coupling is, unlike the chemical shift case, we can actually tune what your dipolar shift is. So what the intermediate regime is can also be tuned. So it's like having a control on what your chemical shift also is. Of course, this is the case, but because the effect is kind of subtle and not very, very cleanly visible over here, it might be difficult to actually implement, use this kind of effect where you change your dipolar couplings by using these scaling factors and then get to an intermediate motion where you can then interpret dampening. My guess is that instead of reader, one of the other methods which do not have the gamma, so which are gamma encoded methods, those probably will be better suited for something like this because they have a much stronger oscillation. For example, let me go to the case of CP. So you see that the oscillation over here is much, much stronger because it's a gamma encoded sequence. So in this case, you might expect the same amount of damping, but as far as I know, nobody has really done this. But it's something that I have thought about, but never really carefully really simulated and see whether you actually see this. So, yeah. But I think this should, yes.
Awesome, thank you. So feel free to for our attendees to continue to ask questions. I'm going to ask another one while I have you here. So, of course, often the choice of experiment is going to be dependent, like very contextually dependent, as you've spent quite a bit of time today talking to us about how it's how your system will impact what the best experiment is for you. But if one is approaching a novel system, a novel biological targets as protein, is reader still kind of the first step in trying to decide where you should go in the kind of data space to explore? We kind of always start with something and then iterate as we learn more, but I'm just curious if that's changed.
So I think if it's a biological system, then, I mean, in spite of the fact that every protein is different, it's really at the molecular level, it's just amide bonds, right? And you're looking at very, very similar groups. So as far as I think the method is concerned, if it's a protein, if it's not something like a paramagnetic protein with very strange groups, and even if it's something like polymers, where we know this just a CH bond or just a NH bond or some other H bond, I think reader is a good place to start always. I will point out, however, is that depending on where you expect your dynamics to be, reader might be completely not the experiment to do. For example, the CH dipolar couplings are going to be of the order of 20 kilohertz, or NH are going to be of the order of 10 kilohertz. So unless you have dynamics that are sort of large amplitude dynamics that occur on a time scale that is faster than the inverse of these couplings, you're going to get exactly the rigid value of. You should be able to measure the coupling, but that's not really the dynamics that you might be interested in. So if your dynamics is on a lower time scale, maybe some of the experiments that people have done that rely on looking at, again, the effects of dynamics on relaxation. So R1 row experiment and R1 experiment, especially for the N15 nuclei and protein, these are quite powerful. And the NERD experiment from Paul Chandra's lab, these are powerful. So millisecond dynamics, that would be probably the experiments that you would try. If you think that, especially some of the cases that I do work with, where you have these large reorientations of transmembrane domains, in that case, reader is the one thing that always comes to my mind. This will be the one that will give you an idea of not only the time scale of the motion, but also the entire amplitude of the motion. And that's why that can be powerful. But in general, I would think that the experiments based on relaxation are still the more general experiments to do.
Yeah, that makes sense. It's a pretty common starting place. And of course, once you have more context, it's easier to choose where
Yes.
where to go next.